Are you taking AP Chemistry? If so, apparently kinetics is a thing. Jennifer Douglas is here to explain to me what kinetics is and help you guys with some hacks for your AP Chemistry exam. Jennifer, what is kinetics?
Well, nice thing that you've asked. It's one unit in the AP Chemistry curriculum, and it actually involves 4 different things. If you can know
that's
these
too many.
4 things.
I want to make it easier. Let's go with what's the what. That's 3 things. I know what graphs are.
Yeah,
and I think
it deals with how fast reactions go, and that's the whole rates part. And it also deals with the mechanisms or the actual steps that are involved in a reaction. And so that's basically it. And so there's not a lot. This is not a difficult unit. This is an easy place to be able to pick up points. And so if you know what to expect when you see a kinetics question, it's going to be really helpful to you to be able to pick those points up and move on to something else.
Well, I don't know what to expect with kinetics. I see there's some great people joining us here in the chat. And some people are apparently excited about this. I'll be in the chat with all of you saying hello. Jennifer, I'll let you get right into it. And if you are enjoying this video, press that like button, subscribe to our channel.
Okay, great. So, John, my screen just went funny. Are you guys seeing my
we do see it. Yep.
Okay, super. So basically, what kinetics is about, there's 4 main areas that they're going to ask you about, and that's about it. If you can talk about collision theory, reaction rates, mechanisms, the actual order of the steps that a reaction occurs in, or a series of reactions, and then lots of graphs, then you can handle whatever's coming towards your way on kinetics. So let's go ahead and get started. I'm going to show you what you need to know for each of these 4 areas. And if you understand the things that I'm going to list for you here, then you're going to have this unit covered. It's an easy one to go ahead and study early and just get it knocked out, because it's not difficult. Kinetics is usually a decent unit for people. So we're going to start with the collision theory, or collision model first. And so that's the whole idea of how does a reaction even occur? And for a reaction to occur, 3 things have to happen. First of all, the reactants have to collide with each other. The second thing is they have to collide in the correct orientation, or with the correct orientation. And then the third thing is they have to collide with enough force to provide the activation energy for the reaction to occur. So it makes sense, the first one, that reactants must collide, because we need bonds to break, new bonds to form, and they've got to be colliding with each other for that to go on. This thing about orientation, that makes sense if you think about it for just a minute. Look at the picture right in front of you. There's 2 different collisions going on. The one on the top has a carbon bumping into an oxygen, and the second one has 2 carbons colliding with each other. Well, only one of those has the potential to result in a reaction, the one that I have circled right here. And that's because if you look at the reaction, we're trying to form carbon dioxide, which has a carbon in the middle and an oxygen on either end. So we need this carbon to bond with the oxygen, and then we need the oxygen-oxygen double bond to break. So that one has the potential to result in a reaction, because the orientation is correct. The orientation means that the carbon is colliding with the oxygen, and those are the things that you're trying to get to form a bond with each other. The second one, this one down here, those will collide, but they won't result in a reaction, or at least not the reaction we're hoping for, because here we have 2 carbons colliding with each other, and we're not trying to form a carbon-carbon bond. So that's what we mean when we say the reactants must collide with the proper orientation. So the third thing is they have to collide with enough force to overcome the activation energy barrier. So the reason that you need a forceful reaction is you're not only forming bonds, you're also breaking bonds. And that collision has to provide enough energy for the bonds to be able to break. Because remember, you have to put in energy, always takes energy to break bonds. And that's what the activation energy mostly is for, is just to break the bonds of the reactants. So anything that you can do that will make the reactants collide more often, or in the proper orientation, or with more energy, will increase the reaction rate. And that's usually where the questions will come from. So they'll say, why does the reaction rate increase when you increase the concentration? And just they want this answer to go in terms of collision theory. So just go back and think of what we just talked about. If the reactants are more concentrated, they're going to collide more often. Therefore, the reaction rate goes up. And then you've got your point, because remember, you have to have collisions to have a reaction. Why does temperature, why increasing temperature, why does that make the rate go up? Well, two things will happen, actually. They're going to, if the particles are going to be moving faster, and since they are going to be moving faster, they're going to have more kinetic energy. That's why they're going to be moving faster, because the temperature will increase their kinetic energy. Then they're going to collide more often because they're moving faster, but they're also going to collide with greater force. So a more forceful collision will give you a bigger amount of energy, higher activation energy. And then for the third one, surface area. So if you have something, think about like a log versus a whole bunch of splintered up wood. If you increase the surface area, there's more places for the reaction to occur. So there's going to be more, this would probably be something where you had a solid and maybe a gas molecule colliding with it, or something that's aqueous. If you increase the surface area, there's going to be more collisions again. So when you're saying, don't just say concentration makes the rate faster, say why. Because there will be more collisions. Or with temperature, there's more collisions, and the collisions are more energetic, so they can provide the activation energy. Or surface area, there's going to be more collisions. And then the two other things they could ask you about is the nature of the reactants. So mostly there, it will be what phase are they in? Two solid things, that reaction, if they're not bumping into each other, they're not going to be reacting. But if they're aqueous or gas molecules, then those are really good systems for a reaction to occur in, because the molecules are moving and they can collide. Also, the strength of the bonds. If they're really strong bonds, maybe something is triple bonded, the reaction rate tends to be slower, because you've got to have enough energy to break a triple bond, not just a single bond. And then finally, catalysts, which we'll bring back up right at the end of this session tonight. Those provide an alternate pathway with lower activation energy for the reaction to occur. They might be something like an enzyme, which holds the two things next to each other, and so that can help with the orientation. But chemical catalysts just provide a different pathway, and that new pathway has less activation energy needed. And so that means that the reaction can occur faster, because more of the collisions will have the necessary energy. And that's basically what you need to know about collision theory. So expect them, if they ask you to talk about why is a rate increasing, think about talking about why, whatever factors they describe to you, and it'll be one of these or proposed to you, why those things make the collisions occur more often or with more energy, and then you'll have your point. So that's the first thing. That's collision theory. The next thing is rate and the rate laws. Now, you guys probably learned in your chemistry course, you should have learned that there's two types of rate laws, the differential rate law and the integrated rate law. This one's the differential one. And, you know, it just doesn't appear all that often, at least not on the FRQ portion of the exam. It used to be on there a lot, but ever since the revision occurred back in 2014, this form of the rate law doesn't appear that much on the FRQ portion. The integrated rate form appears a lot, but I'm going to go ahead and show you both just so that you can wrap your mind around what this is. So what a rate law does is it tells us how rate is dependent upon the concentrations of your reactants. This one right here, the differential one. So you have the reactants A and B, and they make some product C. And you can't tell just by looking at an overall reaction what happens when you increase A or increase B. Does the rate double? Does it triple? That sort of thing. And the reason behind that actually comes up with the mechanism section, which will come up in a minute. Whenever you're looking at a reaction, you're looking at the overall reaction. Think about photosynthesis, for example, you know, where you have whatever it is, carbon dioxide and oxygen making the sugar molecules. That is not occurring in one step. You guys know from taking biology, there's a whole bunch of steps that are involved in photosynthesis or cellular respiration. Well, in chemistry, when we're looking at reactions, we're looking at the overall reaction. So we don't know where the reaction's going fast and where the reaction's going slow. We have to determine it experimentally. So what you end up doing is, on this one right here, is you'll take your reactant A and B and you'll start with it's called this method of initial rates. You'll go into the lab and you'll start with 3 molar, that's your concentration of A, and 5 molar for B. And you'll measure the rate of the reaction. Like it's changing by 20 molarity per second of whatever it is that you're measuring. It could be the appearance of C, the disappearance of A, it could be pressure or absorbance, anything that's measurable. You'll find out what the rate is. Then you go and you run the experiment a second time, and you start with 6 molar A and 5 B. So now look what you've done. You've doubled A, but you've kept B constant. And then you see what happens to the rate. And this is the initial rate. You take the rate really early, right at the beginning of the reaction. And you see that the rate, when you doubled A, then the rate doubled. So it was directly proportional. So that means that A would then be called first order. And then you would run the experiment another time. And this time you keep A constant and you double the concentration of B. But look what happens to the rate this time. Instead of doubling, it went up 4-fold. So we call that a second order reaction. And that's something that you should have learned in your chemistry class already, but it's not appearing on the exam all that often. Instead, what happens is you're getting the integrated rate law instead, or you're getting questions about the rate law that they give you. So I wouldn't say don't know how to do this, but it's not as heavily tested as the other rate law is, recently at least. And at the end of this session, I'm going to go and show you all of the rate questions that they've asked since 2014. And you're going to see that this one doesn't appear all that often, if at all. So this is more likely the question that you'll get from the rate law is something like this. And I think this would be more likely to be in a multiple choice portion. But they would give you the rate law, and then they would ask you, well, what would happen to the rate if you doubled the concentrations of both A and B? And this is an easy question to answer. So if you doubled the rate of A and B, just put the numbers in, put a 2 in for A because you're doubling it, and B is also twice as much, and then just do the math. So it would go up by a factor of 2 times 2 squared. 2 times 2 is 4, times 2 is 8. It would go up by a factor of 8. If we had said, what happens if you triple the concentration of A and double B, and put a 3 in for A, a 2 in for B, so 2 times 2 is 4, times 3 is 12, the rate would increase 12-fold. And that's more like the question that I've seen lately on the differential rate law. The one that they do ask you about, though, is this one right here. It's called the integrated rate law. And it's a different way of finding out what the rate is. These are related to each other. Still going to be talking about the same experiment. So you still have the reactants A and B. But now what you do is you can just learn about one of those at a time. So like starting with A. And what you do is you go into the lab, but you only run one trial this time, or one set of conditions. And what you do is you start with a certain amount of A, and then as time goes on, you start measuring the concentration of A and see how it changes. So obviously it's going to go down since it's a reactant, but you collect time for 5 seconds, 10 seconds, 15 seconds, 20 seconds, and that sort of thing. So the other one, this one, you were just measuring one point in time. You had its initial amount of A and B, and you calculated the rate right at the very beginning, and then you were done. And then you had to change something else. This one, you're calculating concentration now instead of A. You're just monitoring how does A change as time goes on. So you collect all that data, and then you come in here and you make 3 graphs. You graph the concentration of A versus time, and then you calculate the natural log of A and graph that versus time. And then you calculate the reciprocal of A and graph that versus time. So you're only collecting the data for the concentration of A, but then you're just mathematically calculating natural log and reciprocal. And you graph all 3 of those versus time. And if you can remember this little, it's clear thing, it's a little mnemonic device that'll help you. C is for concentration, L is for the natural log, ln, and R is for reciprocal. And those go in order of 0, 1, 2. So if concentration versus time gives you a straight line, it's going to be 0 order. And only one of those is going to give you a straight line. You'll understand why when you take calculus, because you're doing integration and you're finding areas under a curve. On this one, this is a different experiment, and now we've got concentration versus time, natural log, reciprocal. And so you're just looking which graph is giving me the straight line. It's the L1, CLR, and I'm just remembering 0 order, first order, second order. The first order, this reaction is first order with respect to A. It's that easy. This is whenever you see these graphs up here, your heart can leap for joy, because it's straightforward. It's just doing CLR. It's very clear. And if the third one, if the reciprocal gives you a straight line, then it's going to be second order, because remember, it's 0, first, second order. And that's as far as we go. Don't do any more orders than that. So you don't have to graph this, because they know that you were limited on time. They're going to give you all 3 graphs, and they're going to ask you what the order is. And all you're going to do is look and say, okay, the reciprocal is a straight line, therefore it's second order. You're going to say it's second order. And if they ask you why, you're going to say because the reciprocal versus time is a linear graph. And then you're going to move on. It's really easy. And that's about what all they ask you for on the integrated rate law. But just in case they ask you anything else, on your formula sheet, this is a picture of the formula sheet. They have the 3 rate laws for 0, first, and second order. Look, the 0 order rate law is in terms of concentration, and notice it's in the form of a line. That y equals mx plus b. Just rearranged. The first order one is the natural log, and the second order one is the reciprocal. So if they ask you, instead of saying what order it is, and they say, write the rate law for this thing, well, then you would just flip to your formula sheet, and you would be thinking, I'm looking for the one that's a reciprocal, because that one's a straight line. And there it is. It's the reciprocal one right here. Every once in a while, they'll ask you to calculate something using it, but at that point, it's just plugging numbers in, because if you know, for example, that it's a 0 order one, because the concentration versus time gave you a straight line, then they might say that that after 5 minutes had passed, your concentration was 20 of whatever it is, but when you started, that's the A sub 0, it was 50. Then you're just plugging numbers in. Your concentration of, I can't remember what I said, 20 minutes or 5 minutes later was 20. So you put a 20 in here, the 50 in for your initial concentration. You're probably going to be looking for K, and your time would be whatever time I just said, 5 minutes later. So you would just plug those in and solve for K. So the formula is there for you. The only thing is they don't tell you that 0, 1, 2, you can obviously tell that's scribbled in by me. They don't tell you which one's which. You have to remember concentration, natural log, reciprocal, 0 order, first order, second order, okay? And then the other thing is, be careful, watch out in case they don't give them to you in this order, because they don't have to put the concentration one first. You just know concentration is the 0 order, natural log one is the first order, and reciprocal is the second order. So make sure that you're paying attention to which graph and not assuming that they're giving you the concentration one first. This is usually what they do, but they don't have to do that. I want you to notice one other thing that's on the formula sheet, and that's the half-life. Every single one of these, 0, first, and second, they all have half-life equations. There's only one half-life equation that appears on the formula sheet, and that's the one for first-order reactions. That's the only one that is testable on the AP exam. So if they are, this is another big clue, if they start asking you about half-life, it's a first-order reaction, because they have excluded the other 2 from the exam, so it has to be first order. Now you can't say when you're looking at half-life data, because this is the only one you're allowed to test me on. But what you can say, if you look at this reaction for the equation for half-life, notice that the half-life is this number 0.693 divided by the rate constant K. That means that it doesn't matter what the concentration is, because there's nothing in this half-life equation where you put in concentrations for anything. And so for first order reactions, and it's only for first order reactions, the half-life is constant. So that would be a justification. And you'll see in when I show you the questions that they asked on some of the previous years, they give you some half-life data and they ask you what order it is. So in your mind, you're thinking, I know it's first order because it's the only thing they're allowed to test me. So you put down first order, and then you go back and try and prove that the half-life is constant, and you've got that point. It's a nice, easy one to pick up. Notice also, if they give you half-life, you can solve for K, the rate constant, or if they give you the rate constant, you can solve for half-life, as long as it's first order. Okay, so that took us through the first two things, collision theory and what they might ask you about rates and rate laws. Now let's look a little bit at mechanisms. Let's see, where was I? I think right there. So what mechanisms do is remember that photosynthesis step that I gave you, or example that I gave you, that we're saying that photosynthesis occurs in, I don't even know how many steps, but many, 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 many steps it takes for the overall photosynthesis reaction to occur. So we write it as a summary step of here's what we start with, here's our reactants, here's our products, but we skip all the stuff that goes in between when we're writing the overall reaction. Well, what a mechanism does is it tells you the actual steps that are proposed to occur. And so like on an equation or on a question like this one, they might either ask you one of three things. What's the overall reaction, which I provided for you, but if they were asking you that, you would have to you're just doing what you do in math, where you're seeing, all right, I see NO3 on the right, I see NO3 on the left, so I'm going to cancel that one, I'm going to cancel that one. And I've got an NO2 on the left, I've got an NO2 on the right, so I'm going to cancel those two, and you're just going to sum them up that way. So you might be asked to do that, but that's just like adding two equations in math. Get the stuff on the left and the right to cancel. So that's one thing they could ask you. The second thing they could ask you is NO3, is that an intermediate or is it a catalyst? And why? So right here, can you guys see that NO3 is formed in the first step, and then it's subsequently in another step used up? That makes it an intermediate. So an intermediate is something that's formed in one step and then later on is consumed. And that is your justification. What is it? It's the intermediate. How do you know? Because it's formed and then later consumed. And I'll show you one of the catalysts, I think in my next example. So that's the second thing they can ask you. They could ask you, what's the overall reaction? They could ask you if something's an intermediate or a catalyst. And then the third thing they could ask you is, what is the rate law for the overall reaction? Well, remember what I said at the beginning is you can't look at a reaction like this one down at the bottom and know what the rate law is, because you have to determine it experimentally, because you don't know what the mechanism is. Well, if they give you the mechanism, now you're able to write the rate law based on the slow step. And so what you do is you look at the slow step right here, and now you just say that the rate law is rate equals K, our rate constant, times how many NOs do we have? Two of them. So NO squared, that's it. So the rate law for the overall reaction doesn't even include the carbon monoxide. It would look like this. Rate equals K times NO squared. And that's the rate law written based on the molecularity of the slow step. Another thing they could do is not tell you which is the slow or fast step. Instead, they could give you the rate law and ask you which is the slow step. And so you'd be looking for one where you've got NO2 as the two reactants and nothing else. And so you'd say first step one is the slow step. That just reminded me of one other thing, which actually works in your favor. Instead of saying slow and fast step, they've replaced the word slow with rate determining step. So that makes it even more like they're shining, spotlight on that one step to say, look, pick this one, pick this one. It's the one that's determining your rate. So the rate for the overall reaction is going to be based on the first step because that's the slow step, and the other ones are going to occur fast. And so it's kind of like, if you're running a relay race, your slow runner is the one that's going to kind of depend, or the one that's going to determine how well that you guys do at the end, because the slower he goes, or the rate determining step, and they could ask you to determine the rate law for the whole thing. Okay. Now, I just paused for a second because I got a little notification that my internet connection's unstable, but it went away. So I'm assuming that you guys can still hear me. So on the third thing, we're on the fourth thing now, is graphs. We talked about collision theory. Remember, if they ask you about what makes a reaction go faster, you're talking about the number of something that's making the collisions increase more, like there's higher concentration. We talked about rate, which is how fast a reaction goes, and the rate laws. Watch out for those graphs. Remember CLR, 0, 1, 2, 0 order, first order, second order. And half-life, the only thing that they're going to test you on is first order half-life. We've talked about mechanisms. The three things that they could ask you about mechanisms are the overall reaction, which is the slow step, or to write the rate law based on the slow step if they tell it to you. And then also, do you have an intermediate or do you have a catalyst? There's one other thing about mechanisms that they can throw in here called steady state approximation, but I'm going to save that for the end because I want to cover what absolutely you have to know. And then if you want to hear the one other thing, then I'll tell that with you. All right. Next thing is kinetics is a very graph heavy unit. So we've already talked about the integrated rate law with the concentration versus time graph, or natural log, or reciprocal. So that's one set of graphs. The other ones to expect is the energy profiles. You can get this as a thermo question, also as a kinetics question. So if you look back at this question that they gave you before, and they said, pick an energy profile that would match it. Well, whatever the slow step is, that's going to be the one with the highest activation energy, because that's what makes it slow. So this would be a graph that could potentially match that one, because it's got a high activation energy for the first step, and the activation energy for the second one is just little. Remember, the activation energy is the reactants all the way up to the top of this line up here, to where the activated complex is what it's called, or transition state is, where the bonds are breaking and new bonds are forming. That's right at the top of this hill. And then when you go back down here, that's the products from the first reaction. And then we've got another little activation energy, and then the products from the second one. So this one is an endothermic reaction. That's thermo, because the products have more potential energy than the reactants do. But what it tells us in kinetics is that the first step is a two-step process, and the first step is the slow step. So that's something they could ask you. The other thing they might ask you to do is they might have you sketch in the catalyzed reaction or something like that. So if they give you the one that's in red and they ask you to show the reaction of a catalyst, what you need to do, you don't have to show the two-step mechanism part of it, but what you would have to do, because they probably won't be asking you to do both of those at once, but if they ask you to show the effect of a catalyst on an energy profile, then what you have to do is you have to make sure that your reactants start at the same place, that your products end at the same place, and that the only thing that you're doing is you're bringing down that activation energy, because catalysts don't affect the reactants energy or the products energy. They just lower that activation energy. So you would want to show a graph. If they ask you to sketch it in, just sketch in something with a lower hill, a lower activation energy to get you there. Okay. And I just realized that there was a question asked earlier, why did I choose NO2 and why was it raised to the second power? Let me see. Go back to NO2. Okay, so I think you're talking about this question right here and why it was raised to the second power. Yes, this is the question that did it. The reason that I chose that was your rate law is only going to be dependent upon the reactants. So you don't need to worry about the products at all, leave them out, because the products aren't part of the reaction, they're just what's being formed. So that makes it easier altogether. The second thing I'm doing is I'm looking for the reaction that says slow step or now says rate determining step. And I know that's the one that's going to be affecting the reaction rate, because the fast step is occurring quickly. So the slow step is the one that's going to affect the overall reaction rate. So now I know, looking just at step one, I'm looking just at the reactants. So the reason I'm choosing NO2 is because those are my only two reactants. So I raised them to the second power because there was two of them. If let's say that the that step two down here, that this one had been the slow step instead, and they're going to have to tell you that. They'll either say slow step or rate determining step. If it had been step two that was the slow step, then I would have said the reaction rate equals K, my kinetics constant, times the concentration of NO3 times the concentration of CO, because I'm just raising them to whatever their coefficient powers are. And it's that easy. That's all that I had to do. Okay. Tell me if that didn't answer your question, but I think that's all you were asking. So the reason I chose NO2 is I chose the first reaction, and I raised it to the second power because there were two of them. I could have written this reaction like this also. That might make it easier to look at. They could give it to you either way. So there were two NO2s, so that's why I raised it to the second power. Okay. All right, so that got us through, all right, expect energy profiles, expect to sketch in the effect of a catalyst, expect Maxwell-Boltzmann distribution plots. I don't think there's ever been an exam where this graph is not on there somewhere on the multiple choice or on the FRQ portion. Now, this one appears with gas laws, but it also comes up here in kinetics too, because this blue line that I've put in here right here, this is the activation energy. So what has to happen is the molecules have to meet this barrier before that reaction can occur, because that's marking the amount of activation energy that you need. So anything to the left of that line, those molecules don't have enough energy. Anything at the line or past it, they have enough energy. So we've got these two lines here. We've got a blue one and a red one. And what that means is they're at two different temperatures for our kinetics thing. So what I'm looking at right here is I've got to figure out which one is at the higher energy. This comes back to calculus again too. And you'll learn more about this then when you're doing distributions under a curve and that sort of thing. But this blue line right here, notice that I'm just going to take the high point right here and read down, because people tend to get this one wrong because they look here and say the blue is higher, therefore it's the higher temperature, but you're reading it wrong. This is just the number of molecules. The x-axis is what tells us the energy. So that for the most of the blue molecules have this much energy right here. The red molecules have this much energy right here. They have more energy. Therefore, the red line is the one that's at the higher temperature. So watch out for that one and don't go to the one that's higher up on the y-axis, because that's just number of molecules. We want the x-axis, that's energy. And so what happens is, if this is the same sample of a gas, for example, and all you're doing is increasing the temperature, then if you shift that line to the right, it's going to have to come down because you've still got the same number of molecules. So where we care about it in kinetics is if you look at this red line right here, there are more molecules that are underneath that curve. So there's more of the red ones than there is of the blue ones. So the red is more molecules have met that activation energy barrier. And so more of them will actually be able, more of those collisions will result in a reaction. They'll collide either way, but more of the collisions will result in a reaction because enough of them will have the activation energy. So that's a Maxwell-Boltzmann one, and that's how it comes into kinetics. If you see this on gas laws, they could ask you the same thing, which one of these are gases at the higher temperature, which we've just talked about. The other thing it could be is these could be two different gases. This is not related to kinetics. I'm not going to jump to gases for just a minute. At the same temperature, and they might ask you which one is the lighter gas, and the lighter gas might be moving with, instead of saying energy down here, it would say speed. And so just read the axis, the lighter gas is going to be moving faster. So just watch out for that. Most likely it's going to come up on kinetics and it'll say energy down here. All right. So what I want to do is just show you from 2019 back to 2014. What I've done is cut and pasted little pictures of anything related to kinetics on the FRQ portion of the exam. And I want you guys to pay attention to what they're asking you, because this lets you know here's what they care about for kinetics. All right, notice that in 2019, they ask you, as soon as you see those three graphs, you're thinking, oh, I know exactly what this is. This is CLR, and there's concentration, natural log. Look at, this is one where they changed the order. There's my concentration, there's my natural log, and this one right here is my reciprocal. That's the one that's a straight line. Therefore, I know what the order is, and I can answer a question about it. Notice they also ask you about mechanisms, and here they have it labeled for you, slow step and fast step. Okay, so they ask you about integrated rate law, and they ask you about mechanisms. How about in 2018? Okay, they gave you a graph of concentration versus time, and that's not a straight line. So that lets us know it's not zero order. But they certainly don't expect you to go graphing the reciprocal and the natural log to find out what order it is. But look, notice what else they gave you. They gave you concentration changing as a function of time here. And notice, let's start with 0.1. Where's half of 0.1? It's 0.05. That took 10 hours to get there. So let's take half of 0.05. That's 0.025. It's taking me the same half-life. It's taking me 10 hours each time for half of my sample to disappear. It's a constant half-life. Therefore, this is first order. That's what you're going to be looking for. So anytime they give you concentration and time data, if they don't give you the three graphs, look for the half-life thing that I had told you about. And you guys see what I mean by half-life. Half of 0.1 is 0.05. So that's the first half-life, is 10 hours. Half of 0.05 is 0.025. That took another 10 hours from 10 to 20. Therefore, the half-life remained constant. It's first order. And that's the way that question appeared. All right, here we go, 2017. There's the Maxwell-Boltzmann distribution plot. And look what they want you to do. They want you to sketch in a second curve that shows the distribution at 30 degrees. And this one's 120. So now you know what to do. You need to make it a little bit higher and bring it down here and make sure that you're bringing it, your line down underneath the line of the one that's at 120. So you're showing that there's fewer molecules that have that activation energy under the curve. And notice they ask you about half-life again. It says a radioactive isotope with a half-life of 10 minutes, calculate K. Well, you're thinking, I'm just going to pull my formula sheet up. And where's my formula sheet? Right there. They told me that what the half-life was. I know 0.693. I can plug that in and solve for K. That's all that question was involving. So you just have to know that if they ask you half-life, flip to this formula sheet and plug your numbers in and solve. Okay. Okay, that was 17. We're working our way backwards. Oh, and notice once you have K, it says if 64 atoms are initially present, what's the amount of time you're solving for T that will pass until only one isotope? So you're starting with 64. That's your initial concentration, so to speak. You're talking about atoms this time. You're ending with one. You calculated K. So you're going right back to that formula sheet. You've just figured out that it's first order because it has a constant half-life. Where's my formula sheet? Right here. If it's first order, then you can plug in the 64 for your initial, the 1 for your final, because you're solving and you found your K already and you're just solving for T. So that's when they bring that. It's not very often that they have you use the formulas, but if they do, just plug the numbers in and solve. But just make sure that if you're talking about half-life, you know that it's first order. Okay, here's 2016, another integrated rate law. This time, let's see, the concentration, natural log, reciprocal. They've kept those in order for you. That one actually kind of looks like a straight line too, but I think the reciprocal one is the one that definitely is a straight line. Therefore, we know it's 0, 1, 2. It's second order. Make sure you start counting at 0. It's 0, 1, 2, not 1, 2, 3. We don't do third order. And then here's 2015. It's another graph. It's CLR. See, did they keep it? Let's say instead of concentration, they gave us absorbance. Who cares? It's the same thing. Absorbance and concentration are directly related. So it's absorbance, natural log of absorbance, and reciprocal. So we can tell 0, 1, it's first order. And that's what the question asks you about there. And then all the way back to 2014, they tell you the half-life was measured, and it's shown here. And you're thinking, am I supposed to try and throw this into the gas law thing? Because they gave me a volume, they gave me a temperature, they gave me a pressure. I know R, but no, it's something easier than that. Look, they gave you half-life. It's the same. It's the same. It's the same. Every time that your temperature was the same, the half-life is the same. It's first order. That's all that you had to do for that question. Why'd the half-life change down here? Well, the temperature went up. So therefore, it took less time for the reaction to occur. The reaction was going faster, and that's why the half-life changed, because the temperature changed there, but the constant half-life. And you guys, that's it. That's what they've asked on the FRQ portion since 2014. We just went back through all the years. Last year, those questions were not allowed to put online. Those are still secure questions, but very similar sort of things. Okay, that got us all the way through. The only thing that I didn't cover was this thing called steady state approximation. So I don't know if you want to stop listening to me now, because this doesn't come up very often, but I'll go ahead and mention it to those of you that do want to know. So when we go back and look, remember I had those things, the slow step right here. And these were just regular reactions. There's no equilibrium going on. So I just look for my slow step and I write my rate law based on the slow step. Well, every once in a while, they'll throw in this thing where the first step, and it has to be one that precedes the slow step, is this fast equilibrium one. And you see it equilibrium, and they label it fast equilibrium for you so that you can see that that's going on. I just saw the side of my picture. It looks like I'm sitting in the dark. There's actually light in my room, but it's getting better each time. Anyhow, not related to kinetics. So the second step, though, is the slow step. And this time, they want you to write the rate law for the overall reaction. Well, the problem is if I write my rate law based on my slow step, I would say rate equals K times N2O4 raised to the first power, because there's only one of those. And that would be my rate law based on the slow step. But look at what N2O4 is. It's an intermediate. I just realized I forgot to show you guys what a catalyst is. I'll go back and do that in one moment. But if it's an intermediate, you're not supposed to have intermediates in your rate law. So you've got to get rid of it. And the way that you're going to do it is this thing called steady state approximation. Again, doesn't come up that often. So if this is kind of freaking you out, skip it. Well, it's not going to be that big of a portion on the exam. But if you want to try and pick up one more point, that was the rate law that I wrote. Rate equals K times N2O4. And I wrote that based on my slow step and just including my reactants. There's only one of those, so it's just raised to the first power. I can't have an intermediate, so I've got to get rid of it. So what I'm going to do is go back to my fast equilibrium, and I'm going to write my equilibrium expression where I do products over reactants. All right, I've got that. So I've got my rate law, and I've got my equilibrium expression for the first step. Now I need to try and rearrange my equilibrium expression and make it in terms of N2O4, because I'm going to try and substitute something in there for N2O4 to get rid of it. So if I rearrange this equilibrium expression and let's see, I guess I would multiply both sides by NO2 squared. So I can get rid of it over here as a denominator and bring it up on this side. Then I've got something I can substitute in for my N2O4. So I've got N2O4 is my equilibrium constant times this thing, NO2 squared. So then I can go ahead and plug my equilibrium expression times NO2 squared right in there for N2O4. And now I have a rate law that's gotten rid of the intermediate. That's called steady state approximation. You only have to worry about it. It's going to come up if there is a slow step after a fast equilibrium. I think I only remember that happening one time since 2014. So it's that I remember, and I might be remembering wrong, but it's not if it's on there, it's not heavily tested. Everybody misses it. But that would be really good for you guys because it's really not that hard to do. You're just rearranging a math thing and substituting it in, but you have to show it this way. On the really old exams, they kind of let you eyeball it and say, oh, I see N2O4 is the same thing as 2 NO2s over here, so I can just substitute in. They want you to go through this series of steps now. You don't have to know that it's called steady state approximation, but that actually is what it is. Okay, I'm going to go back one more time because as I was talking, I realized I forgot to mention what a catalyst was. So where's my catalyst example? Here it is. All right, remember we said what an intermediate was? That was something that was formed in one step, like NO3 here, and then subsequently consumed. A catalyst is just the opposite. So my catalyst example, where's that guy? Right here. If I use it in one step, like see, I'm using B, and then it's later reformed. So it's the opposite of the intermediate. The intermediate is formed and then later consumed. The catalyst is consumed and then later reformed, because catalysts are never all the way used, or they're never used up. They're always reformed later on. That's how you'll know it's a catalyst. It's formed, it's consumed and then later reformed. So that's the difference between intermediates and catalyst. Okay, so I'm looking at the question. When you first showed us the graphs for the different orders, there were different curves on each graph, but I heard you say whichever one is straight is the right graph. That's right, because what happens is, like this one right here, for example, if you do concentration versus time, you collect that data in the lab. Then you go and you graph your concentration versus time, you graph your natural log of concentration versus time, and you graph the reciprocal. It's all the same data. You've only collected it one time, but you're just graphing concentration. Then you calculate natural log and graph it. Then you calculate reciprocal, graph that. Only one of those will be straight, and whichever one is linear, and whichever one is linear is the right answer. So they'll give you all three. You're picking the linear one, and it's 0, first, second order. Concentration is 0, linear, natural log is first, and reciprocal is second, 0, 1, 2. Okay, I think, John, that got me to the end. So I'm going to stop screen sharing unless anybody had any other questions that I needed to flip through here. I'll actually leave that on for a second.
Great. Yeah, I'll pull this down for just a second and let you find maybe some light.
Really
Total darkness. And everyone, I want to thank you for coming. I hope that this session's been valuable for you. Remember, this is the third session we've done as part of our series for AP Chemistry. I'm about to go live in just a few minutes with Emily Glankler from Antisocial Studies for AP World. We're posting live reviews in all sorts of subjects in the next couple of days, and that will round out the month of March. But on this channel here, we're going to be going live. So definitely subscribe to our channel and follow us on Instagram and TikTok. That's where we put a lot of our updates about our schedules, and definitely check out the links in our description. And thank you, Winifred, by the way, for asking all these great questions in the chat tonight. So Jennifer, any other parting words of advice for students taking the 2021 AP Chemistry exam? How do it's late March, we've talked about this before, but how do I study?
So this is what my students are going to do. We have one more week when we get back. We're on spring break this week. Then we're going to come back and wrap up electrochemistry, and then we're going to start our studying. And what I'm going to do with them is what I just did with you guys tonight, in that there's so much that we cover in all of the units. What you want to do is nail it down to, if you see that they're asking about rate, or as soon as you see they're asking about kinetics, think, what are the 4 things that I know about kinetics? And don't worry about the wording on the exam. Just think, I know that they've got to be asking me about collision theory, a reaction rate, a mechanism, or something with a graph. And I know that's it for kinetics. And then do the same thing for equilibrium. I'm going to have to write products over reactants. I'm going to have to stick numbers in there, that sort of thing. So go through each unit and kind of like maybe like you're playing some kind of Pokemon game, and this is your bag of tricks that you've got, or your, whatever you have at your disposal, the lightning bolts, whatever. I'm probably making horrible references here, but anyhow, what you want to do is every time you see it's a certain topic, think they've got to be asking me about one of these 3 or 4 things. And so if as soon as you see that it's thermo, think I'm going to be calculating delta H, and I know 5 ways to calculate that. It's got to be one of these. I'm doing kinetics. they've got to be asking me about something, rates and mechanisms, or a graph, something like that. So if you can narrow, as you're going through, kind of summarize what the themes are. And so that when you see a question in the back of your mind, think it's got to be one of these 5 things. That'll give you the confidence to go ahead and answer the question. The second thing I would say is, we are a mathy, sciencey class. Don't get distracted by words that you haven't seen before. Like if they had put the word steady state approximation, don't think, I don't even know what that is. You don't have to know the word they're using. They may phrase it differently. If you're looking at a graph, what's, like something like a energy profile or whatever. They're either asking if it's endothermic or exothermic, or they're asking you something about activation energy or sketching a catalyst. So don't let the words distract you from what they're asking you, because they're very consistent on what's being asked from year to year. One more thing I think I would do is go back, and you can pull up the exams from each year. Go pull up the 2014 FRQ, work through it, and then do the 2015, do the 2016, and you'll start to see patterns on that exam where they ask you the same sorts of things each year. I'll stop there.
Great. Well, thank you, Jennifer. Thank you. We're getting some questions about what we'll be doing. We will be posting some more information about lives and other resources for you guys. Remember, check out the link in our description, not for chemistry, but for a lot of subjects. We've got study guide packs, practice tests. We even have courses where you can send us your essays and we will grade them. It's all on our website. Check that out. Jennifer, thank you so much for coming to tonight's session. And for guiding us through kinetics. I feel like I'm going to get a 5 now.
There you go.
So excellent. Everyone, have a great night. Thank you for coming. And we will see you on the Marco Learning YouTube page, Instagram page, everywhere you are on